Hello students, in the last two lectures we have looked at the basics of spectroscopy. In this lecture we will look at some specific features of spectroscopy which is quite common to different kind of spectroscopy. There are two things which we are going to discuss. One is resolution and second is intensity. So, first one is spectral resolution. A spectral resolution is a measure of the ability to separate nearby features in wavelength space, and generally spectral resolution is given by lambda divided by delta lambda, where delta lambda is minimum wavelength separation of two resolved features. So, suppose there are two peaks, and if we can separate these two peaks, or if we are able to separate these two peaks which is quite close to each other. So, that is basically what we mean by spectral resolution. So, for example, here you see this is the output versus wavelength. Your delta lambda is generally given by your full width at half maximum, which is known as FWHM. So, full width means this width, we are talking about this width at half maximum. What does that mean is this is your height and half of this is this height, half of this is this height. So, if suppose this is h and this distance is your h by 2, then your width, spectral width at half height is called delta lambda. Delta lambda can be measured in data and depends on data analysis. It can be limited by diffraction, slit width and detector sample. So, if spectral resolution is high, what does that mean is you will be able to separate two very close peaks. So, a good resolution is important criteria in a spectroscopy. The spectral resolution will depend on line broadening, and line broadening can be due to several factors. So, if line broadening is high, it means resolution is low. So, broad peak has very low resolution, whereas a sharp peak has very high resolution. So, what you are looking in the spectroscopy is that you should get very sharp peaks, and so you will be able to distinguish between two nearby peaks. The factors which can affect line broadening is your Heisenberg uncertainty principle. A line can broaden due to Doppler effect, line can broaden due to pressure or power or saturation broadening, and it can also broaden in electrical or magnetic fields. We will go one by one and see how does these 5 factors affect the broadening of signals. So, first we will discuss about Heisenberg uncertainty principle, or this uncertainty is basically due to wave nature of the particle. So, basically here what we will look at, that whether position can be specified exactly. So, here we show wave function for a free particle of momentum p. So, we are looking at wave function of a single wavelength with a fixed momentum. A wave can have two parts, one is real and imaginary part having same wavelength. They are shifted by the both real and imaginary part are shifted by 1/4 of wavelength. So, this is 1/4 of the wavelength, 1/4 of the wavelength, which is equal to 90° shift in the phase. These two waves do not interfere either constructively or destructively from each other. for this particle with well defined value of momentum. So, here since there is one wave of one wavelength, so it has well defined value of momentum. Here your wave function extends from positive infinity to negative infinity. What does that mean is, your since probability of finding a particle is proportional to a wave function square. So, you can find particle everywhere, you can find particle between positive infinity to negative infinity. Now, suppose we take 5 waves of different wavelength, which is shown here. So, what we have done is, we have taken 5 wavelength of 1.2, 1.1, 1.0, 0.9 and 0.8, and phases are adjusted such that all of the peaks of wave match at 0 on the horizontal axis. So, we can see here, you can see here that waves are matching at x is equal to 0, but if you go away from x is equal to 0, because of different wavelength, they are not going to match up at other positions. At some places, one wave has a positive peak while other has negative peak. So, you can see here, for example, here you see this has, the black one has your positive peak and this one has negative peak. So, at some position one wave has a positive peak while other has negative peak. What does that mean? That means that at x is equal to 0, since all of the wave are in the same phase, so they add constructively, whereas near x is equal to 0, we are talking about this region, the waves are still pretty much in the phase, whereas in the regions between 10 and 20 and minus 10 and minus 20, the difference in wavelengths makes some of the wave positive. So, some of the waves are positive, where some of them are negative, So, there is a significant cancellation. So, if we take combined wave, it will look like this. So, at x is equal to 0, since there is constructive interference, all waves add up, and so there is a maxima. So, you can see there is a maxima. Near 6 and minus 6 also, 6 and minus 6. So, this is 6 and this is minus 6. You can get some maxima, but that will not be as large as maxima at x is equal to 0. In the region between 10 and 20 and minus 10 and 20, so 10 and 20 and minus 10 and 20, there is a significant cancellation. So, your value amplitude will not be that much high, or amplitude will start decreasing. Now, think of if there are 250 waves, what will happen. So, this is the example where 250 waves are taken of different wavelength between 0 and 4, and phases are adjusted so that at x is equal to 0, there is a region of maximum constructive interference. In this case, if you take very large number of waves, what will happen is there is much larger cancelling at other position of x, and you can see almost 0 at other position of x. So, the amplitude of superposition is dying out, going towards plus 20 or minus 20. And so, what this tells you, that when we have a large number of waves constituting your electromagnetic radiation, what does that mean is your delta P will be large, In that case, you will be able to specify the position of the particle. specify the position of the particle. That is what is shown in this two diagrams, which tells you about relationship between spread in momentum and spread in x. So, when you are taking large number of waves, it means your spread in momentum is high, because each wavelength corresponds to a single momentum, and since there are large number of wavelengths, and so there is a spread in momentum. In that case, the spread in x is low, and when we have only one wave, it means only one lambda, which corresponds to one momentum. So, you are talking about one specific momentum. In that case, you cannot locate your particle, because it can go from minus infinity to plus infinity. Spread in p and spread in x is related. So, if there is high spread in p, what does that mean? There will be a small spread in x, and if there is a small spread in momentum, it means there is a large spread in x, and this is the basis of Heisenberg uncertainty principle. So, Heisenberg uncertainty principle tells you that delta p, which is your spread in p multiplied by delta x, which is spread in position, is greater than equal to h by 2 pi. What does that mean is that it is impossible to specify both the momentum and position of particles simultaneously with arbitrary precision. So, if spread in momentum is high, then only you can be able to tell what is the position of the particle. If there is a spread in position, then you will be able to tell what is the momentum, but both p and x cannot be specified simultaneously. So, higher the uncertainty in momentum, it is easier to locate the particle and vice versa. So, this uncertainty principle has also a generalized form. So, what does this tells you? That for any two pairs of observables, the uncertainties in simultaneous determination is related by this equation. This is equation which is generalized equation of uncertainty principle, that uncertainty in observable O1 multiplied by uncertainty in observable O2 is greater than equal to half, and then this commuting operator O1 and O2, where O1 and O2 is given by O1 into O2 minus O2 into O1. So, this is your what is known as commutator. So, if this is equal to 0, then what will happen, that this will be 0, and then you can precisely determine two observable at the same time, but if this is not equal to 0, then you cannot precisely determine the observable O1 and O2 simultaneously. So, the second example of this Heisenberg uncertainty principle is between two other observables, energy and time, and again delta E into delta T will be greater than equal to h by 2 pi, because they do not commute with each other, and so delta E into delta T is not equal to 0. And this is related to a spectroscopy, because what we generally look at is in a spectroscopy is a broadening of signal which is related to delta E or delta nu. So, if delta is high, it means, or uncertainty in E is high, it means your peak is broad. You can convert delta E to delta nu, and delta nu is again related to delta T. Delta T is your what is known as lifetime. So, if lifetime is higher, it means delta nu or delta E will be higher, and it means peak will be more broadened. Similarly, you can relate this equation with uncertainty in wavelength, since your frequency is c by lambda. So, del nu by del lambda is minus c by lambda square. So, we can simply write delta lambda is equal to delta nu into lambda square by c, and delta lambda, and then if you put this from your Heisenberg uncertainty principle, you can get delta lambda. So, this is your uncertainty in wavelength, and that is related to delta t, which is lifetime. So, delta lambda is, you can say, is inversely proportional to delta t. It means if there is higher uncertainty in lambda, then delta t must be low, or if lifetime is smaller, then uncertainty in lambda is higher, whereas if lifetime is your, if lifetime is delta t is your high, then your delta lambda will be small. Line width depends on lifetime of the excited state. Longer the lifetime of the excited state, sharper will be the spectral line. So, if delta t is high, it means delta lambda is small, and so peak will be sharper, peak will be sharper. So, Heisenberg uncertainty principle tells you about your broadening of the peaks. So, if you go from electronic transition to suppose NMR, what happens that in electronic transition, your lifetime of the excited state is very small. Lifetime of the excited state is very small, since there is a larger difference between ground state and excited state, and so there will be the peaks obtained in electronic transition is quite broad, particularly in UV visible spectroscopy. And if you go to NMR, since the energy difference between two levels, ground state and excited state, is smaller, and so lifetime of excited state is high, lifetime of the excited state is longer, and so sharper lines are obtained. And so, NMR is a high resolution spectroscopy, whereas UV visible is low resolution spectroscopy. Apart from Heisenberg uncertainty principle, Doppler effect can also affect the broadening of spectra. So, wavelength of a spectral line is dependent on the velocity of source relative to the observer, and the relationship is given here, that is delta lambda by lambda naught is equal to V by C, where delta lambda is wavelength shift, or you can say that line broadening, and lambda 0 is wavelength of the source when it is not moving. V is the velocity of your source, velocity of the source relative to observer, and C is your speed of light, speed of light. So, what you can see is there will be a rate shift if source is moving away from the observer, source is moving away from the observer, and there will be a blue shift when source is coming close to the observer. So, you can see here that in this case, this is your source waveform and this is your receiver waveform, and here your with increasing distance this lambda increases and there is a rate shift, whereas if they are moving towards each other, then there is a blue shift, there is a blue shift. So, this is not only applicable to light waves, it is also applicable to other kind of waves, for example sound waves. So, if source is moving away from the observer, there will be rate shift, and if source is coming closer to the observer, there will be a blue shift, and this is well known Doppler effect. This is well known Doppler effect. So, now think of that if you are trying to look at a spectra of some sample, and suppose we are you are an observer. So, what will happen is that some of the atoms of the sample will come towards you and some is going away from you. This is because of your Brownian motion. This is because of Brownian motion. So, something which is coming towards you is basically your blue shifted, the one which is going away from you is red shifted. So, what will happen that this is when there is a no shift. If you are looking at the spectra of those molecule, so what will happen? Some of the molecules are just at the position at just a random position, and then what will happen? Some of them are going away from the detector and some are coming towards the detector. So, those which are going towards the detector will have a blue shift, and those which are going away from the detector will have red shift, and so your line will be broadened. So, this is the position, the one which is moving away from you will shift to longer wavelength, and those who are going towards you will shift to a smaller wavelength, and so there will be red shift and blue shift, and so whole spectra will get broadened. So, in the detector, individual red shifted and blue shifted emission lines merge with the unshifted lines to produce broadened spectral lines. Other things which shows the effect of Doppler or Doppler effect on the your spectra is when you are looking at the spectrum of rotating star. So, what will happen is that your light is coming to you from this side and from this side. Okay? From two sides light is coming to you, and that is how you are observing your rotating star. So, what will happen? Suppose there is a rotation from this side to this side. So, basically the light which is coming on this line, what is happening? It is going away from the observer, and when it is going away from the observer, what does that mean? It is red shifted. What about this ray, this light? So, this is basically coming towards the observer, and so this will be your blue shifted. So, the one which is going away from detector is red shifted, those which are coming towards you will be blue shifted, and thus whole range of spectra will be obtained, and that is why you see a continuous spectrum. So, this is about the light, effect of Doppler effect on the light. What about sound source? So, now you see here, if it is moving towards you, so car is moving towards you and there is a your siren, and so this will appear to be of smaller wavelength and high frequency to this person, whereas it will appear to be of longer wavelength and low frequency to this observer. This is just because for this observer your source is moving away, whereas for this observer it is moving towards the car is moving towards the observer. So, apart from Heisenberg uncertainty principle and Doppler effect, apart from Heisenberg's uncertainty principle and Doppler effect, you have pressure broadening. The spectra can broaden due to pressure. So, when an excited state atom is hit with another high energy atom, energy is transferred which changes the energy of excited state and hence the energy of photon emitted, and this results in line width broadening. And you can see here that the gas under low pressure will show this kind of a spectra, whereas at intermediate pressure you can see that there is a broadening happening, and this line looks like this under intermediate pressure. At high pressure you see again this much broadened, and at extremely high pressure you can see almost continuous kind of a spectra is obtained, almost continuous kind of a spectra is obtained. This broadening is Lorentzian in shape, and that will be given by this formula. FWHM is full width at half maximum and nu naught is your peak center in frequency units. Peak may be broadened due to electric and magnetic field. So, large broadening of lines of absorption due to transverse magnetic field tuned by changing distance between ferrite magnets. So, this is shown here and you can see that if you go from, so this is distance between ferrite magnets and this is magnetic broadening, and you see you are going from the distance, you are going from 13 centimeter to 8 centimeter. As you decrease the distance between ferrite magnets, the line is getting broadened, You are basically increasing the magnetic field from 5.5 gigahertz to 8.4 gigahertz, and there is a broadening of peaks. Okay. Continuous emission is an extreme example of electric and magnetic field on broadening of multiple wavelengths, and these are the your black body radiation curve for different kind of lamp at different temperature. So, these are the few of the factors which affect the resolution of the peaks or they broaden the peaks, and so it is important to understand what are the factors which can affect the broadening. Now, the second thing which is important in almost every kind of spectroscopy is intensity or signal to noise ratio. The intensity of spectral lines depends on transition probability between the two states, population of states, and finally, your concentration and path length of the sample, which is given by Beer-Lambert law. So, we will go to one by one and see how does they affect the intensity of your spectral lines. First thing is your transition dipole moment. The transition probability between two states, for example, you take wave function I or state I to state F is given by your this formula, where mu Fi is transition dipole moment and this is your psi f tells you about wave function of the final state. This operator mu operator is your transition dipole moment operator and this is your wave function of ith state, and this integral is known as transition dipole moment integral. This integral is referred as transition dipole moment integral. The transition is allowed only if the transition dipole moment integral is non-zero. So, if this integral is non-zero, it means transition is allowed. If this integral is 0, then transition is not allowed. So, whenever we go and discuss various type of spectroscopy, we will go for example, rotational spectroscopy, we will take wave function of rotational levels and then we see in under what condition this dipole moment integral is going to be non-zero, and under those conditions the spectra or transition that your rotational transition is going to be allowed. If your transitions are allowed, then you expect that signal intensity should be high. The second factor which can affect intensity is population of states. So, if there is a difference of population between two states, ith state and f state or ground state and excited state, your intensity will be higher. So, higher the population difference, higher will be intensity, lower the population difference, lower will be intensity. Now, the distribution of particles in different states is given by your Boltzmann distribution law, which tells you that n by n naught is equal to exponential minus E x by k T, where E x is difference between two energy levels. So, the energy levels which you are considering where transition is happening. So, the E x is difference between energy level of the state from where transition is taking place and the state where transition is happening, So, E x is difference between two energy levels. N 0 is population of the ground state, T is temperature and K is Boltzmann constant. So, you can see that population in excited state, which is your N, is going to be affected by the difference between two energy levels and temperature. So, if difference in energy level is high, it means your population is going to be, population in the excited state is going to be lower, and if temperature is high, it means your population is going to be higher in the excited state compared to the population in the excited state at lower temperature. So, there are two factors which is going to affect the population of different energy levels. So, spectroscopy signal intensity increases with increase in population difference between the two states. And the last factor is concentration and path length of the sample, and this is given by Beer-Lambert law, which tells you ln I by I naught is minus epsilon Cl, where I is the intensity of the light after absorption, and what you can say is after passing through the sample, where I naught is the intensity of light before passing through the sample. Epsilon is molar extinction coefficient, C is concentration, L is path length. So, epsilon would be high for transition which are allowed transition, and C is concentration, L is path length. So, if concentration is high, then again absorbance is going to be high. Depending on delta E values, signal of some of the spectroscopy or spectrum will be high, some of them is low. Now, question is how to improve intensity or signal to noise ratio. As we discussed in the last slide, that concentration can affect the intensity. So, one of the easiest way is increase the concentration of the analyte, and that should increase the signal, but sometimes it is not possible to increase the concentration, and so what can be done? Another way is to increase the number of scans. So, take spectra once, take another time, third time, fourth time. So, increase the number of scans and add all the signals. And third is collect the data in time domain mode and do Fourier transformation. I will go and tell you about advantage of the second and third factor on improving intensity or signal to noise ratio. So, now let us look at increase in the number of scans. Signal will increase to n time after n summed scans. So, if you have taken signal once, twice, thrice or four times, and then you add the signal, then it will, your total signal will be 4 times signal taken in one scan. Whereas, noise being random will contribute sometime positively and sometime negatively to total noise. So, what happens, since your noise is random, so it will not be true that every time noise or at every point noise will be positive. Sometime it can be positive, sometime it can be negative, and so the total noise is not going to be like n times the noise. So, basically what happens that noise accumulate less rapidly and it goes up by root n time if number of scan is n. So, net gain in signal to noise ratio is root n time. So, basically by increasing the number of scans you can increase the intensity or signal to noise ratio of the spectra. Now, let us go to the third factor, which is basically based on mode of collection of signal. Mode of collection of signal, and based on this spectroscopy is also divided into two. One is your time domain spectroscopy and the another is your frequency domain spectroscopy. So, first we will discuss frequency domain spectroscopy. Frequency domain spectroscopy is often used when signal to noise ratio is high. Signal to noise ratio is high, and basically what you are doing here, you are plotting absorbance or intensity versus wavelength. So, what you are doing here is you have started getting the signal at every lambda or wave number or frequency. So, it is like playing a piano where you are going and pressing one piano at each time. So, this key, then this key, followed by this key, followed by this key. So, you are going one at a time from one part to another part and looking at the signal. So, signal is detected at number of frequency in continuous fashion. So, what you will see is a spectra like this. So, here your intensity is plotted against each wavelength or each frequency in a continuous fashion. Now, let us go to time domain spectroscopy. This is the spectroscopy where what you are looking at is absorbance intensity versus time. So, you can see here, this is generally used for low sensitive spectroscopy. What you do that in contrast to your frequency domain spectroscopy, you press all the keys at the same time, and so basically you are supplying a mixture of number of frequency, or you are applying the sum of different frequencies to the sample at one time. And this is particularly useful for insensitive technique, because time required for one scan is reduced drastically. So, suppose there are 60 keys and pressing one key takes 1 second time. In frequency domain spectroscopy, if you are going from 1 to first key to 60th key one by one, then it will take 60 second time. While in the time domain spectroscopy, since all of the key is pressed at one time, it means that it is going to take only 1 second, only 1 second. So, basically you are reducing the scan time by 60. So, it is time is basically the time taken in frequency domain spectroscopy divided by 60. And what is the advantage? You can again go back, do more scans, and then you can increase intensity by root 60 times. Now, question is how to transform time domain data to frequency domain data. So, once you obtain time domain data, you need to convert it to frequency domain data to get information out of it. So, you need to convert time domain data to frequency domain data So, basically you need to process the data to get the frequency domain data. There are two key points in Fourier transformation. One is a time domain spectrum is basically a combination of several cosine waves of different frequency and amplitude. Suppose there are two chromophores, they absorb at two different lambda value. So, your time domain spectrum is sum of cosine waves of two different lambda value. So, you can think of, suppose you are taking NMR. So, if you have 5 protons and they absorb at different wavelength. So, your signal will be, time domain signal will be combination of 5 different cosine waves, 5 cosine waves of different frequency, 5 cosine waves of different frequency. So, once you understand that, now you will utilize one of the property to convert time domain spectrum to frequency domain spectrum, and that property is that cosine waves of different frequencies are orthogonal to each other. What I mean is that if you take cosine wave of frequency W1 and multiplied that by cosine wave of wavelength of frequency W2, and then if you add up between t is equal to 0 to t is equal to infinity, then you should get a value of 0. If omega 1 and omega 2 is different, W1 and W2 is different, then if you multiply cosine wave of frequency omega 1 and cosine wave of frequency omega 2 and then sum up from t is equal to 0 to t is equal to infinity, then you should get 0. And this property is used to convert your time domain spectrum to frequency domain spectrum. So, let me show by example. So, this is your cosine wave of 15 hertz. So, this is the way your cosine wave of 15 hertz looks like, and here your amplitude, and there is a time, and sometime it is at higher amplitude, then it will go to 0, then negative amplitude, and then this is the way its amplitude changes with time. Now, think of, if I multiply this by this cosine wave of 15 hertz by cosine waves of different frequency, then how should this look like? So, first we have multiplied that by 5 hertz, and you see it looks like this. So, some part has positive amplitude, some part has negative amplitude, whereas when we multiply by 10 hertz, again you can see there are some part which has positive amplitude and other part has negative amplitude. But when we multiply by 15 hertz, then everything has positive amplitude, whereas again if we multiply by 20 hertz, then this part has positive amplitude, this part has negative amplitude. And now, if we sum up from t is equal to 0 to t is equal to infinity, if we sum up from t is equal to 0 to t is equal to infinity, what amplitude you are going to get is 0. Sum of the amplitude will be 0. If we multiply cosine wave of 15 hertz with cosine wave of 5 hertz, this will be 0 in this case also, and this sum of amplitude will going to be 0 when we multiply by cosine wave of 20 hertz. In only one case it is not going to be 0, when you multiply cosine wave of 15 hertz with cosine wave of 15 hertz. You multiply by any cosine wave or cosine wave of any other frequency, then 15 hertz, total amplitude will be 0. Total amplitude is going to be 0. So, that is what we mean by the cosine waves of two different frequencies are orthogonal to each other. Now, let us think of that if our time domain data is function of two different wavelength. Okay. So, suppose I take 15 hertz cosine wave or 30 hertz cosine wave. So, this is your wave for 15 hertz and this is your amplitude versus time for your 30 hertz cosine wave. If we add up, we are going to get this signal. So, your time domain data is going to be something like that. It is going to be sum of different sum of cosine waves of different wavelength, sum of cosine waves of different wavelength. Okay. So, let us think of if I multiply the sum of or the wave consisting of 15 hertz and 30 hertz cosine wave by your 15 hertz cosine wave, then what you get? You see, most of the time it is towards positive side. At very small places it is going to be negative. But if you look at, if I multiply by 10 hertz cosine wave, there are lot of time it has a negative amplitude. When I multiply by 30 hertz cosine wave, then again it has positive value most of the time, positive value most of the time. So, what you expect is that if your cosine wave or if your time domain data is sum of cosine waves of 15 hertz and 30 hertz and then you multiply by cosine waves of suppose 1 to 60 hertz apart from two places or apart from two cosine waves, one with frequency 15 hertz and one with frequency 30 hertz, its amplitude is going to be 0 if we integrate between t is equal to 0 to t is equal to infinity, t is equal to 0 to t is equal to infinity, and that gives us a very good tool to convert your time domain data to frequency domain data. So, look at this picture and here there are three waves. There are three waves, one with 10 hertz, 120 hertz and 40 hertz. So, these are three waves of different frequency 10 hertz, 120 hertz and 40 hertz, and this is your combined signal. This is your combined signal. If we do Fourier transformation, so again we are going to different value of frequency and we are multiplying that by this combined wave function and then integrating amplitude between t is equal to 0 to t is equal to infinity. Basically, we are adding up, what you will get is 0 at other values except at 10 hertz, 40 hertz and 120 hertz. So, if you do Fourier transformation of time domain data, you will get a signal only at 10 hertz, 40 hertz, 120 hertz if your time domain data is mixture of three waves of frequency 10 hertz, 40 hertz and 120 hertz. So, this is the basis of your Fourier transformation. So, we have looked at some special features of spectroscopy which is quite common to different kind of spectroscopy you will come across, and now we are going to look at some problems related to this. So, first problem is, so suppose lifetime of an excited stage is given, you need to calculate what is the natural line width of the transition from ground to excited state, Just take this Heisenberg uncertainty principle, this equation from Heisenberg uncertainty principle, that uncertainty in frequency multiplied by your delta t multiplied by delta t, which is basically lifetime, is equal to 1 by 2 pi. here lifetime is given, that is 100 nanosecond, and so it is quite easy to calculate what will be the uncertainty in frequency value, and that is going to be 1 by 2 pi into delta t. Delta t is 100 nanosecond, and so 1 into 10 to the power minus 7 second, and so you will get this much delta nu. So, this is your natural line width in frequency unit, natural line width in frequency unit, and you can calculate natural line width in wave number unit by simply dividing this c by delta nu, and this comes out to be 5.31 into 10 to the power minus 3 meter inverse. Okay, next question is broadening based on Doppler shift, broadening of peak based on Doppler shift. So, what is Doppler shifted wavelength of a red traffic light, which has basically wavelength 680 nanometer, approached at 60 kilometer per hour? And the second part is estimate the lifetime of a state that gives rise to a line width of 0.2 centimeter inverse. So, your Doppler shifted wavelength can be calculated from the Doppler effect. Delta lambda is equal to lambda 0 into v by c, lambda 0 v by c. V is the velocity of source and c is velocity of light. Velocity of source is given 60 kilometer per hour, and that's you can change in meter per second, and that comes out to be 16.67 meter per second multiplied by this wavelength, and this is wavelength of your source when it is not moving, when your detector is not moving, and this is your c velocity of light in meter per second, and what you get is this much. So, this is equal to this much nanometer. So, this is your Doppler shift, this is your Doppler shift. The second question is estimate the lifetime of a state that gives rise to a line of width 0.2 centimeter inverse, and it can be calculated similarly what we done in question number 1. So, we use Heisenberg uncertainty principle. So, delta nu can be calculated, and from that delta nu bar can be calculated, and that comes out to be this per second, this per second. Okay. So, your delta t will be given by 1 by 2 pi into delta nu, and then you can get the value of lifetime, value of lifetime. So, line width is given in wave number unit. You need to calculate your line width in hertz or second inverse, and then you put this into this equation, Heisenberg uncertainty equation, that delta nu into delta t is 1 by 2 pi, then you can get delta t, which in this case is 26.5 picosecond. Now, second question, delta E is given, and then you need to calculate what will be the ratio of population at room temperature, ratio of population between higher state to that at ground state at room temperature, and that can be calculated using your Boltzmann distribution law, which is given by this equation, n by n naught is equal to exponential minus delta E. So, just make this correction, minus delta E by kT, where delta is your difference between two energy levels, difference between two energy levels. So, basically you are looking at the difference between ground energy state and the higher excited state, higher excited state. So, this is your delta E, and this is your T is temperature, which is in this case room temperature. So, let us take at 298 K, K is Boltzmann constant here, then what you are going to get is exponential minus 0.462. So, you can calculate n by n2, which comes out to be 0.62. So, few multiple choice questions. Among the following spectra, sharpest signal is observed in UV phase, rotational, vibrational and NMR. So, again you can go back and look at Heisenberg uncertainty principle, which tells you that if lifetime is high, then you can get sharpest signal, and lifetime depends on the energy difference between two energy levels. So, if energy difference is high, then lifetime is going to be small, because your molecule in excited state wants to come back to ground state very rapidly, but when energy difference between two levels are small, then there is a less tendency to come back to ground state. So, lifetime is going to be high, and so lifetime is going to depend on delta E value, and delta E value is smallest for NMR out of all these 4, and so lifetime of excited state is going to be largest in case of NMR, and so sharpest signal is obtained in NMR. Sharpest signal is obtained in NMR, and thus NMR is known as high resolution technique. Among the following spectra, broadest signal is observed in, again you have to look at the energy difference between different energy levels corresponding to a particular spectra. So, in UV vis there is a transition between electronic energy levels where delta is very high. If delta is very high, then lifetime is going to be small, and if lifetime is small, you are going to get a broad signal, and so broadest signal is obtained in UV vis spectra. Okay, next question is that assume that excited vibrational levels are 100 centimeter inverse above the lowest energy level, then ratio of molecule in typical excited vibrational level to that in ground state at 298 K will be. So, again we will apply your Boltzmann distribution law, n by n naught is equal to your exponential minus delta E by kT. So, delta E can be calculated since we know that the wave number, so we can calculate delta E, and delta E will be given by SC nu bar, and now here you must keep in mind that delta E should be expressed per molecule, not per mole, if you are going to use Boltzmann constant. If you are going to use R value, gas constant R value in place of Boltzmann constant, then you must take delta E in joule per mole, otherwise you have to express delta E in joule per molecule, and if you do that, you can get the value, and the answer in this case is B, which is 8 into 10 to the power minus 3. In the next question, one energy level is given, second energy level, and this value is given in wave number. So, this is 40,000 centimeter inverse, and now again you have to find out ratio of molecules in typical excited vibrational level to that in the ground state. So, ratio of molecule in this excited level divided by molecule in this ground level. So, again we will calculate by same formula, your Boltzmann distribution law, n by n naught is equal to exponential minus delta E by kT. Here temperature is 1000 degrees Celsius, you must need to convert this in Kelvin, and when you do that you will get the answer is 2.35 into 10 to the power minus 20. So, just to summarize, various type of spectroscopy and population ratio between excited and ground state is given, and lifetime is also given. Lifetime will tell you about your broadening, and N1 by N0 or ratio between excited and ground state will tell you about intensity. So, these are the various spectroscopy, UV vis, IR, microwave or radio frequency. The nature of transition is electronic in UV vis, vibrational in infrared, rotation in microwave, nuclear spin in radio frequencies, and the energy of transition is this 120,000, 12,000 in infrared, 12 in microwave, and 10 to the power minus 3 to 10 to the power 1. And if you try to calculate the ratio between excited and ground state, population ratio between excited and ground state at room temperature, this is going to be this value. So, now you can see in NMR almost your excited and ground state are equally populated, almost they are equally populated. Lifetime is lowest in the UV vis and highest in the NMR, highest in the NMR, highest in the NMR. And so, intensity is going to be highest in your UV vis spectroscopy, whereas resolution is going to be highest in NMR. So, UV vis spectroscopy is low resolution technique, whereas NMR is high resolution technique, but NMR is low sensitive technique. It means signal to noise ratio in NMR is going to be low, and to get higher signal to noise ratio in NMR, you need to take more scans, and generally data is collected in time domain mode, and then Fourier transformation is done, and then Fourier transformation is done. So, thank you for listening, and see you